Okay, we're going to continue on to we're gonna go ahead to chapter 15, and then we'll come back to a couple of those chapters before it. This is starting last exam stuff, which is exam 4. Last time we finished up talking about gases and gas laws and partial pressures and kinetic molecular theory of gases. And that was the last chapter for the upcoming exam a week from Wednesday, I think it is, actually. So this is 15, which is solutions, which will be good for some of the stuff we're doing this week in lab. So let's talk about it. Solutions are aqueous solutions, which are homogeneous mixtures. And a solution, which is a homogeneous mixture, are typically the ones that get the aqueous symbol next to it. A solution is basically made up of 2 parts. One part is the solute, which is the smaller part of the solution. The other is the solvent, which is the larger part of the solution. And you do need both of those things there to make up an actual solution. So the solute is typically the stuff that is dissolved in the larger part, which is the solvent. So when you make a solution that's a solid and you dissolve it in something like water, which is our solvent, it will make our solution, which is aqueous. So a reminder that we probably talked about this previously, the difference between something that is a pure liquid and something that is aqueous. Something that's a pure liquid is a pure substance like water. So if you have water just by itself, that would be considered a liquid. If you took water and you dissolve something like sodium chloride in it, that salt would dissolve and it would make a sodium chloride solution that would have the aqueous symbol. And again, the solute is always the name of the solution. So if you're not sure what the solute is pretty much whatever the name of the solution is. So if I have a sodium chloride solution, then the solute is sodium chloride. If I had a calcium chloride solution, the solute there would be calcium chloride. Probably if it is ionic, in a lot of cases, the solvent will be water. And water is a really good solvent, as we'll talk about, for things that are ionic. Works really well with it. A solution, again, is a homogeneous mixture, which means everything does mix throughout. So all those solutions used in the lab, all those sort of dropper bottles of stuff are solutions made by really taking something and sort of dissolving in a lot of cases with water. Now, as I mentioned, water is a really good solvent for a lot of things, but it's not always the best solvent for all things. And that's really because, again, water is polar. So there's really 2 sides to water. There's the oxygen side, which is more negative, and there is the hydrogen side that's more positive. And that's a result of water being polar, like we talked about when we did Lewis structures. The overall sort of unequal sharing of electrons creates a dipole moment in water, where we do have a negative side and a positive side together. So that is a really good thing when it comes to something that's ionic, because when it does go into water, it's going to create ions. And what happens is our cations, which are positively charged, once again, will be sort of attracted to the negative side of water. And that's going to help it dissolve. And our negative ions, or anions, would be attracted to the positive side of water there, which would be our hydrogen side. The way that ionic compounds sort of dissolve in water are just in general how molecules sort of interact with each other, are basic interactions of basically positive and negative attraction to one another. So pretty much all molecules, the way they interact is through that opposites attraction between the opposite sides. So in the case of water here, the positive side attracted to the negative ion, and the negative side of water attracted to the positive ion. And that also happens with something like water attracted to itself. When you get two waters together, the positive side of one water is attracted to the negative side of another, and they do what is sometimes referred to as hydrogen bonding, as we'll talk about a little bit more about in just a second. But that is the way that two water molecules basically interact with one another. And that is really, as we'll talk about here, some of the basis of why things are soluble in each other, why things mix together, and why other things do not mix together when we get interactions that are very, very different from one another. So what helps with things mixing, like an ionic compound with water, is that ability to interact the same way water can interact with itself. That's also why something like water is a really crappy sort of solvent for other things, like non-polar things. Like you might have saw last week when you threw your iodine in your water, it did not dissolve. And that's because iodine is non-polar and water is polar. So they're trying to use different things. And that does not work very well to interact with one another. So when we do dissolve something like an ionic compound with water, this is essentially what happens. This is essentially, kind of what the little aqueous symbol that we put next to these guys mean. When we do something that's ionic, it's really a strong electrolyte, which means when it goes into water, it's a lot of ions that are floating around, and those ions are hydrated by the water molecules that are surrounding them. It does basically two things. It helps it dissolve, and it also keeps those two ions apart from one another. And that's a pretty good thing because the attractive force between the two ions, between the positive ion and the negative ion, is probably one of the strongest interactions that you could have, is those ions kind of being together. So just by the sheer amount of water that's in obviously some water that you're using as a solvent, it's enough to help pluck off really these ions from one another and start to surround them. That's also why when we make a solution like a sodium chloride solution, it is a homogeneous mixture, which means it's really just a physical change that's happening. There's no real chemical reaction happening, although sometimes people mistake it for a chemical reaction because they see the sodium chloride disappear and they think it must have reacted or did something. You just can't see it at this point because there's just so much water that's in there. It's no longer visible to us. All the ions are basically surrounded by these waters and trapped within the water sort of matrix that it sort of disappears. But we know it's still there, like some of those earlier experiments that you did with the evaporating dishes at the end. You put them up on a beaker of water and let it sort of evaporate off all the water. If we were to do that in this sort of sodium chloride solution, if we evaporated it off and heated it up, all the water molecules would essentially evaporate away, and that would leave nothing in the way for these two ions to come back together. And if you remember those sort of earlier experiments, at the end you had sort of a residue in your evaporating dish, and that was the two ions being able to come back together as you got the water pretty much out of the way. So the water in this case, as it dissolves, does really those two functions. It helps keep those ions really separated from each other so it doesn't go back and reform the solid, and also obviously helps to dissolve. Questions on that there? And that's essentially what happens here. As you can see, water molecules come in, they start plucking off these ions. This is what an ionic compound looks like in the solid form. It's a very ordered sort of arrangement of the ions where it maximizes the positive negative attraction between those ions and minimizes positive and positive ions being near each other, or negative and negative ions being near each other. And here's sort of in action. So you can see all the water molecules, which are the red and the white circles, coming in basically and starting to pluck off some of our ions from this ionic solid. Just grab one right there. Now it's going to get fully hydrated, and that's going to help it dissolve. We help the process of dissolving, right, by stirring. Throws a bunch of water molecules all over that solid, more surface area for those water molecules to sort of interact with. Also, it increases the energy, right, as well as you're stirring. And that's also why if you increase the temperature, typically you get more solid to dissolve because you're also increasing the energy, which is going to allow those water molecules and also the ionic solid to gain more energy and start moving away from each other a lot easier and go into the solid phase as well. So how these molecules sort of interact with each other does go back to sort of bonding and the relationship of what type of bonds you have in different types of compounds. And these hopefully should be a reminder for you at this point. Again, an ionic bond, as we've talked about many times, is a metal and a non-metal where we have transfer of electrons from the metal to the non-metal, which forms our cations and our anions. And again, what's holding that together is that opposites attract, electrostatic attraction. And that's different than covalent bonding, where we have some aspect of sharing of electrons, usually between two nonmetals. And as we talked about with bonding, the sharing may be equal sharing or maybe unequal sharing, depending on the situation. And what determines whether or not it is equal or unequal sharing in a covalent situation is really that electronegativity difference, right? So if we have a difference in electronegativity that is 0.4 or less than 2, it will create a polar bond where we will get a separation of charge and we'll have something that is partially positive and partially negative, which is really important. If we have less than 0.4 or 0.4 or less, is considered a nonpolar bond, which means essentially the electrons are going to be shared equally, and there's not going to be a positive or negative side to that bond. And that has a really big effect on how molecules can interact with each other. So for example, the way really molecules interact with each other are intermolecular forces. And again, the basic interaction is really positive and negative attraction between molecules. And there's 3 types. There is hydrogen bonding, which is a really strong attractant. And that is a bond between hydrogen and nitrogen, oxygen, or fluorine. So if you look at the periodic table, nitrogen, oxygen, and fluorine are the upper right of the periodic table, which means they are very highly electronegative. They have high electronegativity, and that means that when they do join up with hydrogen, they're going to create a pretty good polar bond. Just for a reference point, if you remember perhaps the bond between hydrogen and fluorine we did, difference in electronegativity, it had a difference of like 1.9, where we kind of cut off to ionic and transfer of electrons at 2, so that creates a really polar type bond. And it's really important, in order for something to be able to hydrogen bond, it does need to be polar, and it does need to have hydrogen directly bound to one of those 3 elements in order for it to hydrogen bond. It cannot, for example, hydrogen bond just because it has hydrogens. If you have something like methane here, which has a bunch of hydrogens, has all these hydrogens here, it cannot hydrogen bond. Again, because the carbon-hydrogen bond is nonpolar, and that hydrogen is not directly attached to a nitrogen, oxygen, or fluorine. So it cannot hydrogen bond even though it has a bunch of them, but something like water can. And if you took something like, say, methanol here, looks something like this. And when we look at something like methanol, it has kind of 2 parts. It has like really a non-polar part, which is where the carbons and hydrogens are. And it also has a polar part where we have this OH bond here. And that's going to be a polar bond. And because that hydrogen is directly attached to an oxygen, that part of that molecule can actually hydrogen bond. So when it reacts with something like water, which has pretty much the identical bond in it, the positive side of one will be attracted to the negative of another, and these guys will be able to hydrogen bond with one another. And I think you did that last week. So you should have saw your methanol and your water really kind of mix together okay, because they should be able to hydrogen bond. And will form really one layer in that case because they were miscible basically in each other. And that part of that molecule, which happens to be an organic molecule, methanol, that small polar part makes a really big difference having that bond there in terms of it being soluble in water or not being soluble in water. If we kind of take something like our methane down here, it is not going to be soluble in water because it cannot hydrogen bond. And what methane will want to use is what is referred to as dispersion forces. And dispersion forces are weak, temporary forces that mainly non-polar molecules use. As opposed to really strong attraction, which is what kind of polar molecules use. So in general, there's a couple ways dispersion forces could work, but one very common sort of way is this sort of situation where you have a nonpolar molecule, which basically means it's neutral. It does not have a positive or negative side to it. But what can occur in this case is the electrons which are flying around in this particular molecule, they all could decide to go towards one side of the molecule versus the other. So if all the electrons decided to sort of head to the right there, what that's going to do is temporarily create a charge in this nonpolar molecule, where the negative charge would be where those electrons kind of went to. Positive charge would be the side of the molecule where they did not go to. And now if that molecule is still near this other nonpolar molecule, that's going to cause the electrons in this guy to go to the opposite side. And now this second molecule, which also normally does not have a charge, will gain a temporary charge. Now these two really neutral sort of nonpolar molecules will temporarily gain charges where they can interact with one another. And they will be able to sort of interact and bond, in a short period of time. This will all sort of fall apart and new ones will form as the electrons return to their normal sort of distribution. And as they return to their normal distribution, that bond will sort of break apart and some new ones will form, and those will break apart and some new ones will form. And that's why these are sometimes referred to as really temporary sort of forces, because it does require something to happen, like the electrons to go to one side of the molecule or the other. Or you could achieve the same effect by rolling in an ionic compound or a polar molecule near a nonpolar one, and temporarily it will be able to sort of get that separation of charge that occurs. It is temporary because a polar molecule, no matter what you do to it, like water, a polar molecule will always have a positive side and negative side. So no matter what you do to it, it's good to go. It's ready to bond that way. It doesn't have to wait for something to occur. And that's why it's a much stronger force, because it's just good to go and it will never change. So if you have water, it's always got a positive side and always has a negative side to it. In the middle is sort of what is referred to as a dipole interaction, and that's also what a polar molecule will use. That cannot hydrogen bond. So you can have a polar molecule that does not have the ability to hydrogen bond, but is still polar, which means it still has a side that's more negative and a side that's more positive. So that is what is referred to as dipole, and that's basically just two polar molecules that basically have that attractive force. So out of these three sort of interactions, once again, this is our strongest interaction. This is our weakest interaction. And dispersion forces are typically what we see with organic compounds. If you have any familiarity with organic compounds, many of the first several are pretty much gases like methane, propane, butane. And that is because they're pretty much all carbons and hydrogens, which means it doesn't take a lot of convincing for them to just kind of break apart and go into the gas phase. And that's why they usually will be gases. That's also why if you continue on and take organic chemistry, they usually throw you in the fume hood when you do the labs, because a lot of organic molecules are very volatile, which means that they start out as a liquid, but doesn't take a lot of convincing for them to go into the gas phase. And a lot of them are flammable, so they don't want those things. Like you might have used last week, hexane and heptane, right? The stinky stuff. The reason you can smell it is because it goes into the gas phase pretty easily, right? Which is why you should keep the lids on and underneath the fume hood. And it's also flammable, which is why you probably hopefully didn't have any Bunsen burners out when you were using any of those things. But a lot of organic molecules are like that. And that's why they put them in the fume hood, because very quickly they could kind of go into the gas phase with not a lot of convincing that's necessary. So these intermolecular forces and the type of bonds that there are on particular molecules plays a really big effect, obviously, in how things interact with one another and how they're able to interact with each other, and why some things cannot interact really well with one another. So let's talk a little bit about things and how they're interacting. Things that are soluble in water. So if something is soluble, when we talk about a solid in a liquid, that's usually referred to as being soluble. If the solid will basically dissolve in the liquid part. If it will not, is typically referred to as being insoluble. As you probably saw with your liquids that you mixed, if you take your two liquids and they do mix together, sometimes people refer to that as being miscible, which means they basically are soluble in each other. And immiscible are when two ones do not mix together. So if you have two liquids that don't mix, you will see different layers basically happening. And if all the liquids do mix together, they will look like one layer. So ionic substances are definitely soluble in water, because they'll be able to do that interaction that we saw earlier, where basically the ions will be surrounded by the positive and the negative side there of water, which will help it dissolve. But there are some non-ionic substances like sugar and ethanol, which are soluble in water. Ethanol looks just like methanol, but with an extra carbon. So this is ethanol. And once again, it really has kind of two parts. It has this kind of non-polar part, which is not going to work really well with water. But once again, sort of the redeeming quality here of this molecule is that it has this OH bond, which once again is a hydrogen directly attached to an oxygen, which means it's able to hydrogen bond. So when something like ethanol and water come together, the positive of one will be attracted to the negative oxygen of the other, and it's able to hydrogen bond, which makes something like ethanol really soluble in water, and also methanol really soluble in water, which is also something you should have saw in that experiment, that those two did mix together because of the ability basically to hydrogen bond. Now, solubility does definitely decrease with the size, for example, of organic molecules like this, with the size of the nonpolar part. So small guys that have like this OH group are very soluble in water because of that interaction. But if you were to just pile on the nonpolar part with a ton of carbons and carbons and carbons and lots of carbons, and the rest of these, I won't draw them all, but the rest of these are basically just hydrogens all the way through on the carbon. This part here is now nonpolar. And we still have this little part here that's polar. So what happens in this situation is, as you build out more of that sort of non-polar side to these molecules, the solubility drops dramatically to pretty much nothing. Something like this would not be very soluble in water, although it does have that OH bond where it can interact with water. The problem is the non-polar side is so big, it gets in the way. So it doesn't allow water and everything to kind of get in there to interact well with this particular molecule here that I drew. The other problem is when you have something that dissolves or mixes with water, what you essentially have to do is replace water and water interactions, which is pretty much what you have going on before you put anything in water to dissolve it. You have to replace those interactions with very similar types of interactions. So although this is a very similar interaction at the end there, it's just too big to work well with water, which is a relatively small molecule. So I sort of like it to, you know, if you try to park a car in a garage, it should get in there okay. But if you try to park like a semi truck in a garage, yeah, you get some of it in there, but not going to work so well. Again, it's just too big to fit in that area. And that's sort of what's happening here. It's just too big to mix in with all the smaller water molecules, and it has too big of a non-polar size. So in the case of these sort of organic molecules like these, which are alcohols really, when you get to about more than 5 or 6 carbons attached there, pretty much they lose their solubility and they're not very soluble at all. The opposite of that is true as well, though. If you happen to have a molecule that has more OH groups in it, that actually will increase the solubility of it. So if you have something where there happens to be multiple OH groups on a particular molecule, even if it's a little bit bigger, it actually will increase the solubility, because pretty much everywhere there's an OH group, that's going to give a place for water to interact well with that particular molecule, and it's going to increase the solubility. So that's what we see here when we do look at this guy, which is our methanol. Once again, doing our opposite attract, our hydrogen bonding here. This is our ethanol. Again, same idea. Opposite charges here. But when we do take something like oil with water, they are not soluble in each other, because pretty much oil is nothing more than long chains of carbons attached to carbons, which is obviously a nonpolar bond, and carbons attached to hydrogens, which is also nonpolar. So because it's nothing but carbons and hydrogens, which is all nonpolarness, and it's really large, it is not going to mix well with water. And typically what happens when you put oil and water together is they will separate out from each other, as water is more polar and oil is more non-polar. So you typically see the organic or non-polar guy up there on top, and your aqueous polar over here. And that brings up an idea when we talk about solubility and things mixing, that is referred to as like dissolves like. So things that, as I mentioned earlier, can interact with other molecules the same way that they interact with themselves through those intermolecular forces will be soluble in each other. When you try to mix things that really are using two different types of forces, intermolecular forces, to interact, you will run into trouble. So that usually means when we talk about solubility or things being soluble, if you take something that's ionic with something that's polar, you're good to go, because it's going to do the positive negative sort of attraction. If you take something that is polar and polar together, you should also be good to go. And the one that sometimes people miss is the nonpolar and nonpolar things will also be soluble in each other, because they're both using the weakest type of interaction, but they're both using the same type of interaction. They're both using dispersion forces. So these nonpolar and nonpolar things will work well together. That's why, for example, if you remember maybe an earlier experiment when you did the halogens, and there was like a top layer where things like Br2 was, you know, I2 and so forth, and there was sort of a bottom layer, and you're looking for the color to change in the top layer to the bottom layer to see if that reaction took place. Up in top, we use something like hexane or heptane up there, which is nonpolar, and that's why up in the top layer we had our Br2, our Cl2, and our I2 up there, which are also nonpolar. So those things are really soluble in each other. And on the bottom was more of the water layer, where we have things like sodium bromide, for example, or sodium chloride, which was on the bottom layer. And that's why those ionic sort of guys were more soluble on the bottom. Why water is a great solvent for things that are polar and ionic, but a really crappy solvent for something that is non-polar. And also, again, why you saw that it would not dissolve your I2 crystal the other day, because I2 is non-polar and water is polar. So again, they're using, one is trying to use dispersion forces, one is using hydrogen bonding, and over the long period of time, they have no way to maintain that, because dispersion forces are temporary and hydrogen bonding is a sort of fixed situation where it's always good to go. So for the short period of time, they could sort of interact, but over the long period of time, they will sort of separate out from each other, kind of like oil and vinegar salad dressing. You can mix it and it will mix for a short period of time. But as you leave the bottle, right, everybody starts to separate out from each other because oil is non-polar and vinegar is polar. It has that OH group. It's basically acetic acid, what we sort of similar to what we saw there. So because of that, over a long period of time, they can't maintain that interaction and they will separate out from one another. So you do run into trouble in terms of insolubility when you kind of cross over polar and non-polar. So when you cross over into that mixture, you're really not going to get things to mix really well with one another. Any questions on that there? So up here is sugar. As you can see, it's a little bit larger of a molecule, but one thing that helps its solubility tremendously is it's pretty much littered with OH groups all around it. So everywhere there's an OH group, that's going to give it an opportunity to interact well with water, which obviously makes sugar quite soluble in water. On the bottom is pretty much what oil looks like. And as I said before, that is pretty much just carbons and hydrogens together. And that's going to be non-polar. Going to try to use dispersion forces versus hydrogen bonding, not going to interact really well, and it's a really large molecule. So that is typically what we would see. Our oil layer non-polar up on top, our water layer there on the bottom, where that guy is not going to fit well with the water and water interaction that occurs. So let's talk a little about solubility and how things are soluble in each other. As I mentioned before, if something is said to be soluble in water, that means pretty much when you mix them together, everything should mix together. You should make pretty much a solution or a homogeneous mixture. Should not have any type of solid that's there. And in case of a solid and a liquid, you would expect the solid to dissolve. And obviously a liquid and a liquid, you would expect it to basically just look like one layer if you mix two liquids together and they're soluble or miscible in each other. If something is insoluble in one another, if it's a solid with a liquid, you would not expect the solid to dissolve. And obviously, as I mentioned earlier, if it was two liquids together that did not really mix, you would see this different layering that would happen, and you would have something that's immiscible. Now, there is a limit to the solubility of one substance in another. So, for example, if you're trying to dissolve a solid in something like water, it is based on temperature, and at a certain temperature, there's only so much that you could get to dissolve in there. So even if something is technically soluble in water, you can't just put a ton of it in, for example. So something like sugar, which if you took a couple of sugar packets in a cup of water, it would definitely dissolve. If you got like the Costco size of sugar and dump the whole thing into your glass of water, obviously at some point that sugar is not going to dissolve. You can sit there and stir all day. It will just continue to pile up at that point. So solubility is based on temperature. And as we'll talk about, typically if you increase the temperature, you can increase the solubility of a solid in a liquid. And usually vice versa. If you kind of lower the temperature, the solubility of a solid in a liquid typically will kind of decrease as well. Now, gases are always soluble in one another, and that is just a process of what is happening because they are in the same container and they are flying around. That means that they are constantly mixing with one another. So they're said to be soluble with each other. Some liquids are also soluble in each other. So again, our polar and polar liquid is going to be soluble. Our non-polar and non-polar liquid will be soluble in each other. And again, it's only sort of that crossover, the polar to non-polar, that you would run into some trouble. So that idea of like dissolves like is really important in terms of how they interact with one another. At a higher temperature, we have a larger solubility of a solid in a liquid. So at a higher temperature, that means, again, there's going to be much more energy involved. And in order for things to sort of go from the solid state to the, say, liquid state, you need more energy. So as you get more energy, even the solid guys are going to start moving around a lot more. water molecules as well will start moving around a little bit more. That's going to allow the dissolving process to occur a lot easier than at a lower temperature where things have a lot less energy, so they're not moving around. Remember that when something goes into the solid phase, it is an exothermic process, which means energy needs to be released. That way, pretty much all the molecules lock into each other and become a solid at that point. As they release their energy, they don't have as much energy moving around. At a lower temperature, there's a larger solubility of a gas in a liquid. And at a lower temperature, our gas molecule should be traveling slower, which means because it's traveling slower, it's going to stay in the liquid part for a lot longer period of time because it's not moving around as fast. And vice versa. Obviously, if you increase the temperature of a gas molecule, it's going to basically shoot out of the liquid part, right? Because it's going to be traveling a lot faster. So it's not going to stay dissolved in the liquid part for as long of a period of time. In addition, the solubility of gases depends on pressure. The higher the pressure, the larger the solubility of gases. And that is because Boyle's relationship is if I have a high pressure, I will then have a small volume, which means in my small volume, my gas molecules are definitely near each other for a lot longer period of time, which means that they are going to be mixing for a lot longer period of time, and they're going to be much more soluble in one another. This is also pressure has an effect on the solubility of a gas in a liquid. At higher pressures, you have a greater solubility of a gas in a liquid. That's what is sometimes referred to as Henry's law, kind of the soda can explanation. In soda, you have like CO2. And before you pop your can of soda, it's under a lot of pressure, which means all your CO2 molecules are in the liquid part of it. When you pop your soda open, your can of soda, you see fizzing sometimes, right? And that is the escape of the CO2 molecules from your water part of your soda. And that is because the two things just happened. You obviously lowered the pressure by popping the can open, and you also gave it an escape route, right? For those CO2 molecules to basically escape. And that's going to be much less soluble now in that liquid part than it was before you kind of opened, bless you, the lid. Also, why your soda goes flat after a while when it's open, because as the CO2 goes out, air comes by and blows it away, which means at some point you have no more CO2 in your liquid part and you taste it and it's very flat, right? Because there's no bubbles basically still in there. There's no gas at that point. It all has escaped through the opening. Any questions on that there? So there are a couple of ways that we do describe solutions. One way that we describe a solution is what is referred to as a saturated solution. And a saturated solution is one where we have pretty much the maximum amount of solute or solid that will dissolve at that given temperature. So pretty much we're exactly at the point where if we put solid in there, it will dissolve. But if we hit that point and put any more solid in at a saturated solution, it will not dissolve at that point. So kind of like the sugar example, you could keep adding sugar and it will dissolve. Again, at some point it will dissolve and then stop dissolving. And that's probably a saturated solution at that point. An unsaturated solution is pretty much the opposite of that. You have not reached that point yet. So if you have an unsaturated solution, you have a small amount of solute in that particular solution. And if you wanted to dissolve more of it in there, you could by just adding more solid, and it should continue to dissolve. And it should continue to dissolve until you reach a saturated solution or a saturation point. So at the saturation point, which is where a saturated solution would become, at that point, it would no longer dissolve, and obviously it will start piling up at that point. You can increase the solubility, as we talked about, by increasing the temperature, and you can create another type of solution, which you did probably saw a demo of last week, which is a super saturated solution. And in a super saturated solution, you have way too much solute dissolved in it. It is a really unstable solution because of that. So typically how you make a supersaturated solution is you make a saturated solution, and while you're making a saturated solution, you actually heat it up. So as you're heating up, what that means is you're going to be able to get more of the solid to dissolve. So like your sodium acetate demo from last week, they heated that up. That allowed them to dissolve more of the solid sodium acetate in that solution, and they will heat it and continue to dissolve more. At the point where they're done sort of dissolving and heating it, they typically will then shut the heat off and you let it cool back down. And you could do that, just let it cool back down naturally. You could throw it into an ice bath if you're careful. But what happens is, as the temperature from the hot temperature and it starts to cool back down, what's going to happen to the solubility of your solid in there is it's going to start to decrease. The problem is it's a little too late at that point because it's already dissolved in there. So it's already in the solution at that point. So in addition, you're also kind of evaporating off some of the water when you do that. So it creates this really, really unstable type solution that you could take one crystal, whatever you dissolved in it, and that's enough to sort of tip it over the scales and go, too much solids dissolved in there, and all the solid will come out of solution. Or if you're not really careful, it's so unstable that sometimes when somebody goes to do that demonstration, they take it out and they just knock the flask by accident. And that's enough to cause all the solid to basically come out of solution. So sometimes, you take that little flask like you had, put it down, and that's enough vibration for it to go too much solid, and it will just start to come out by itself. So this is pretty much what was happening in that example demonstration that you did. This should look something like that. That's a supersaturated solution of sodium acetate. It is a solution at this point made by dissolving way too much of the solid in it by raising the temperature and then allowing it to cool back down. And as you can see, they're just going to put one little crystal in, kind of like probably he did, and that should cause all of that solute that's in there to come out of solution because it should not be there at that temperature. There's way too much dissolved in there at that point, so it all comes out. And that becomes rock hard. Perhaps he touched the bottom of the flask, got really hot on the bottom of it. Again, because you're making solid at that point, needs to release the energy to make that solid. The result of that is the flask would feel really hot. Super slow motion, I guess, in case you missed it last week and today. All right, any question on those types of solutions? Now, a couple other ways that we describe solutions. Concentrated solution has a relatively large amount of solute in it versus the solvent. And more often, though, we do use dilute solutions when we're doing any type of experiments. So usually when you buy solutions, they come in more concentrated, sometimes referred to as stock solutions. And we do some type of dilution to make them not as strong. Classic example is, again, if you get like, your drink there from the Thirst Oasis with your ice before you come to class and you drink it, it tastes pretty good, right? Because it's got some ice, it's cold, it's got some syrup and all that good stuff. You leave it in your car and come back after class, all your ice is melted. You go, how bad could it be? So you take a drink, right? And then maybe you regret it, but it doesn't taste the same, right? Because all the ice is melted, all that water is now diluted down that soda, and it's much, much more dilute in that case because of that. So typically when we take a concentrated solution and want to make a dilute solution, the only thing that we're adding is solvent to do that. And in a lot of cases, that solvent is water. Any questions on solutions, solubility, types of solutions? Okay, the next thing we're going to talk about then is concentrations and some different types of concentrations that we deal with when we're dealing with solutions. The first type of concentration is what is sometimes referred to as a percent concentration, and that is the mass percent, or percent mass to mass. And that's basically mass and mass, which is like grams over grams. And it is the mass of the solute over the mass of the solution times 100%. when you do these type of problems, it is really the bottom part that's really important. The bottom part, remember, is a solution, which means there's two parts, and that is the solute and the solvent. So you want to make sure that you actually get the mass of the entire solution and not the mass of just the solvent. And that is because in these type of problems, it's very common that they will give you that information separate from one another. So they will give you the solute by itself mass, and they'll give you the solvent by itself. And it's very common that people will just divide by the solvent because they go, oh, that looks like the larger number, so we'll go with that one. But you want to make sure that you add them together and you get both of those things to get the actual solution. Now, if you had a 3.25% by mass sodium chloride, you can convert it into a usable, which you sometimes want to do maybe in a dimensional analysis sort of approach. That means there is 3.25 grams of sodium chloride over 100 grams of solution. So that is a way that we can kind of convert our percentage into a conversion factor. Just kind of assume that you have 100 of it. Again, it's grams over grams. You also could flip it around and use it in the other direction. 100 grams of solution is 3.25 grams of sodium chloride. So occasionally it's a little bit easier sometimes to use it as a conversion factor rather than plug and chug into the equation, but you can just plug it into the equation as well. It's really the same math, but maybe sometimes easier to see some of the units. So this is one very common sort of percent concentration, which is mass percent. There's a couple of other ones that are also very commonly used, and that is percent volume to volume and percent mass to volume. So let's take a look at those. Percent volume to volume, like in alcohol, is the volume of solute divided by the volume of solution times 100%. This is very much usually milliliters over milliliters, basically volume over volume. The percent mass to volume is kind of like density, is the mass of the solute divided by the volume of solution times 100%. And this is kind of like density, grams over milliliters. So just like the other one, if you had a 3.25% by volume sodium chloride solution, that would mean you have 3.25 milliliters of sodium chloride in 100 milliliters of solution. Or again, you could flip it the other way if you needed to use it in this form. 100 mils of solution, you would have 3.25 milliliters of sodium chloride. And if you had a 3.25% mass to volume, that would mean that you had sodium chloride, 3.25 grams of sodium chloride in 100 milliliters of solution. Or in 100 milliliters of solution, there is 3.25 grams of sodium chloride. So for all these sort of percent concentrations, you can convert them into usable conversion factors. And again, you could just assume 100. Out of these three, I would say it's just the first one that you really have to make sure of in terms of the solution part. And a lot of problems, they will give you the volume of the solution without you having to maybe figure out the solute and the solvent together. On these three here. All right, so why don't you try one here? A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of this solution. So percent mass to mass is what we're looking for here. Yeah, so let's take a look. We're looking for the percent mass to mass. So that's going to be our mass of our solute divided by the mass of the solution times 100%. In this case, it is the calcium chloride here that is our solute, as it is the smaller part. So our solute here going to be 2.5 grams of calcium chloride. Our solvent, which is the larger part there, is going to be water in this case. So our solvent will be 50 grams of water. So remember that it is both of these together when we add them, that gives us our solution. So we want to make sure we do add them together. So it's going to give us 2.5 grams plus 50 grams. Going to give us 52.5 grams of solution. So once again, that is going to be the bottom part. We do not want to use just the 50, which is the solvent. So we want to make sure we do add them together. Top part here going to be our solute, which is that guy. So that gives us everything we need, which means our percent mass to mass here would be our 2.5 grams divided by our 52.5 grams times 100%. And that's going to give us 4.76%. You could leave it percent M/M. You could put something like calcium chloride. It will look good, I think. Yeah. 3 sig figs, 3 sig figs. Any questions on that one there? All right, so let's try another one here and see. Concentrated hydrochloric acid contains 37.2% by mass. HCl. What is the mass of HCl in 35.5 grams of the concentrated hydrochloric acid dealing with percent mass to mass? So in this case, we are given the percent mass to mass, which is 37.2%. We're looking for the mass of our solute, which is the HCl. And we do have the mass of the solution, which is 35.5 grams. Once again, since we are looking for the mass of the HCl, and because pretty much the solute is the name of the solution, that's how I know that that is the solute that we're looking for, and the 35.5 is actually the solution. Because it was, if we say solution, if it was not the solute in this case. So in this case, there's a couple ways we could do it. We could just plug and chug into the equation. We could also kind of convert our percentage into a conversion factor and do more of a dimensional analysis approach. So I'll show you that here. We would then say that this is basically 37.2 grams of HCl in 100 grams of solution. Or you could use it in the opposite way. 100 grams of solution is 37.2 grams of HCl. So since we do have the grams of solution given to us, we could take 35.5 grams and we'll times it by our conversion factor here, since that is the solution. We have 100 grams of solution and 37.2 grams of HCl. The grams of solution will cancel. Will leave us 13.2 grams of HCl is basically dissolved in the solution. So that is, again, the same pretty much if you plugged it into the equation where you went 37.2% equals grams of HCl divided by 35.5 grams times 100%. You would multiply this to the other side and then divide by 100. Which is pretty much what we did over here. So it gets you obviously the same answer that you got here. So you could plug it in to the formula. You could use the percentage as a conversion factor and do more of a dimensional analysis sort of approach. Any questions on any of those there? So these percent concentrations, I will say, are used, probably they are used, but really the most common unit of concentration that's used is really molarity, which is what we're going to talk about next. And that's pretty much, I would say, probably 99% of the time if you're doing something with solutions and you're doing something with concentration type units, molarity is probably going to be the one that you're going to use. So let's talk about molarity and what it is. Molarity is abbreviated with a big M, and it means basically moles of solute over liters of solution. And you could think of molarity kind of like a formula, kind of like the density formula. We will use molarity a lot and solve for any of these three things. So we could use molarity and volume to get to the moles, which is a very common calculation. We could use the liters and molarity to get, the moles and molarity to get to liters. So we can rearrange this, and liters would equal moles divided by molarity. And moles, which is a very common calculation, is liters times molarity. So that is something that we use a lot to convert into moles. And it's really important that when you are using molarity by itself, that you do convert the volume into liters, so that you will get the right unit that you're probably looking for, which is moles. If you leave it in milliliters and you multiply it by molarity, you will not get moles. So if you take milliliters times molarity, sometimes when people do that, they think they get moles, but they do not. They get what are known as millimoles, which are kind of like moles, but 1,000-fold difference. And that's not so good because you do need to divide by milliliters to get back to molarity. So my recommendation is, and probably in most cases, if you're using molarity and you have volume, convert it to liters. You'll be in probably the correct unit that you're looking for. You won't be off by a factor of 1,000. Why do people multiply milliliters times molarity? They get millimoles. That's okay if you then divide by milliliters. So if you take millimoles and divide it by milliliters, the millis cancel, and now you're back to molarity. So that's actually okay in some cases. That's why sometimes people will say molarity is millimoles over milliliters, because the millis cancel out and you basically are left with moles per liter. But the safe thing to do, and probably what you should always do, if you're using volume and molarity together, make sure the volume's in liters. That way you get the right answer. Now, if we have something like 4.55 molar calcium chloride, that means that we basically have 4.55 moles of calcium chloride in a liter of solution. The other important thing when you do calculations involving molarity and where people really screw up is they leave the big M in there. You should pretty much convert it back to moles per liter so that you can see both units. In my experience, most people, when they leave the big M in the calculation, they forget all about the liters part. They have no idea about the volume, where it is, or if there's any volume involved. They just think moles when they see the M, and you will get probably the wrong answer. Or you will probably multiply when you should be dividing, or divide when you should be multiplying. So this way, if you convert it and get rid of the big M up front, like we just did there, you can do more of a dimensional analysis approach, and you can see both units. It will remind you where the liters are. You could also use it like a conversion factor and flip it around the other way if you needed to. The moles always stays with the number, and it's always 1 liter when you do molarity. So my recommendation is get rid of the big M, use both of those units, do it more like a dimensional analysis. And it will also help you if you're not so great on the rearranging here. Just taking a dimensional analysis approach and opposites cancel will allow you probably to do the right math, just in case you rearrange it wrong. Any questions on that there? So if we have a 1 molar solution of sodium chloride, that means basically we have 1 mole of sodium ions and 1 mole of chloride ions in 1 liter of solution. So in a lot of cases, especially dealing with ionic compounds, we are sometimes interested in a particular ion that's maybe floating around in the solution versus the whole thing. So when we have something like sodium chloride here, in that solution, what's really floating around, because it's a strong electrolyte, is really sodium ions freely floating and chloride ions floating around. There is no sodium chloride unit sealed together. So, like I said, sometimes we're interested in maybe some type of calculation about just the sodium ions or just the chloride ions. So when we have something like sodium chloride, when it breaks apart into a sodium ion and a chloride ion, how molarity works is pretty much like stoichiometry here. When we look at sodium chloride, for every one of those units that go for a swim, we pretty much get 1 sodium ion basically floating around in that solution. What that means in terms of the concentration is we take 1 times the molarity, and it would tell us that in that particular solution, there is 1 molar sodium ions, just sodium ions floating around in that solution. We could do the same thing for the chloride. For every 1 of the whole thing, we get 1 chloride ion, which means we will multiply it by 1, and we would get 1 molar. There is the chloride ions concentration. Molarity is not additive, so obviously when you add 1 and 1 on the right there, it doesn't equal 1. So it is sort of the proportion of ions that you get as it goes for a swim into that solution. Now, if we were taking a look at something else like, say, calcium chloride, when that breaks apart, we get a calcium ion and 2 chloride ions in this case. And if we had a 1 molar solution of calcium chloride, we would basically have this happening here. We have a 1-to-1 relationship between the whole thing and just the calcium ions, which means the concentration of the calcium ions would be 1 times 1 molar, which would be 1 molar. When we look at the chloride, though, it is a 1-to-2 relationship. So we get twice as much chloride ions for every 1 that goes for a swim. How that affects concentration is we would multiply it by 2. So 2 times the concentration there would mean that it is 2 molar chloride in terms of its concentration. So as I mentioned before, they don't add up obviously to 1, but basically we get twice the amount of chloride as we do calcium in this case. So it's twice as concentrated in terms of chloride versus the calcium concentration. If it broke apart into like a 1-to-3, it would take 3 times the concentration of the whole thing and so forth. That is really the short version of this calculation. The longer version of this calculation really is just a stoichiometry sort of calculation. If we took, for example, 1 mole of calcium chloride per liter, which is pretty much what the 1 molar means here, and we just do our mole to mole relationship, it is a 1-to-1 relationship. So 1 mole of the whole thing gives us 1 mole of just calcium ions. They cancel. Gives us 1 mole of calcium ions per liter, which is 1 molar, which is how we get to that. If we did the same thing for our other guy, 1 mole of calcium chloride per liter, which once again is what we're starting with. And we do our stoichiometry, a 1-to-2 relationship, 1 mole of the whole thing here gives us 2 moles of the calcium. Moles of the whole thing cancel. Gives us 2 moles of calcium per liter, which is this concentration. So that's essentially where the multiplied by 1 comes from. The multiplied by 2 comes from is that long calculation. But the shorter answer is just multiplied by the coefficient that you get when you break those guys apart into the ions. Again, it's common that sometimes we're interested in not necessarily the whole thing in terms of the ionic compound, just maybe one of the ions that are floating around in there. Any question on how concentration is related to ions here? Yeah. Yeah, I mean, you can actually do the calculation either way. Sort of the top one there is just a really quick, short way of doing it. You basically just multiply by the coefficient because that's pretty much doing the mole-to-mole relationship part of it. But that's really the long version of the calculation, which is on the bottom, and why we just multiply by 1 in that case or multiply by 2 in that case, because that will give you kind of the right mole to mole relationship. Yeah. Other questions? All right. All right, so why don't we try one here? Calculate the molarity of a solution prepared by dissolving 15.6 grams of potassium bromide in enough water to make 1.25 liters. Potassium is 3910. Bromine is 7990. Okay, so let's take a look. We're looking for molarity, which is moles per liter. In this case, we have the mass of KBr, which is 15.6 grams. We have the volume, which is 1.25 liters. So in this particular case, we already have the liters. I will say in some molarity cases, the conversion between milliliters and liters is done a lot. So a reminder that 1,000 milliliters is 1 liter. Although we did not have to use it in this problem, it is very commonly needed to be used. We do need the moles part here to get to our molarity. So we do have the grams. So we would need the molar mass here from the periodic table. If we add that together, it give us 119 grams per mole. So we'll convert our grams into moles. The grams of KBr will cancel 0.131 moles. That's sort of the missing part that we need to get to our molarity. So our molarity here will be 0.131 divided by 1.25 liters. Gonna get us 0.105. You could leave the units as moles per liter as they will not cancel. Or you could write 0.105 big M KBr in this particular case. Any questions on that calculation there? All right, we'll lay it up there for